Welcome to the Inside EVs podcast and the third in a 10-part series of Tech Talks presented by AVL, where there's so much to learn in the exciting and dynamic field of EVs that we wanted to go to a company like AVL. They work across many different areas of electrification, and with many other companies, they're all driving forwards and together an electric future. They work with both startups and the world's biggest vehicle makers. Well, in this series, we've already looked at the various paths to electrification, and coming soon, we'll talk about battery safety and charging technology as well. But today, we're talking about how to build a virtual EV before you even build anything in real life. But even then after that, when a real car exists, how do you know if making a change on one part of the EV, say changing the battery, will introduce problems with another part of the car, say the control electronics or the motors? Well, let's introduce the team who can tell us more. Wolfgang Pontigam is the Global Business Unit Manager. We'll talk to Ryan Ashantel, who's the Team Leader of Development Process, Innovation and Implementation, and Veronica Obersteiner, who is the Project Manager. And so first of all, welcome to the podcast. Let's start off with talking about some background, because although I have been assured this is a simple topic, I suspect I'm going to learn a lot on the podcast today. So let's start with the background of how car makers have traditionally made cars in the past. Who wants to take that question first of all?
Martin, thank you very much for the introduction. So let me take this one first. So when you look at the automotive industry and the development process, right, the whole vehicle car manufacturer industry has now a history of 100 years in vehicle development. So, and when you look at that, they do a lot of things right, and they have learned a lot. And out of that, they have really clear processes in place, where a typical vehicle development process lasts between 3 to 5 years, depending if it's a completely new development or an adaptation of an existing vehicle model. So they have really strict processes. They have really much experience in developing the vehicle out of this history. And a typical OEM, how we see it today, is hardware-centric, organized. So there is a guy who is responsible for the engine, there's a guy who is responsible for the gearbox, there is a guy who is responsible for the chassis, and at the end, everything have to fit and work together. So a traditional car manufacturer is really an expert in integrating all these parts, because at the end, the sum is more than the single components. But what we also see is that our industry is in change. It's much in change, because there is a lot of new technologies at the moment in introduction. So that means electrification is there, right? It's not a new thing, it's there. Then we have autonomous driving, which is pretty new, and there is a heavy investments also there. What also means that there is a change. We see a change in the approach, how the OEMs develop vehicles. So they have to change. There's a change on the one hand side on the mindset. There is also a big change into the processes, because if you see new entrances, how they approach the vehicle development process, they're coming from a completely different industry as we see it, especially a few of them coming out of software. And they doing vehicle development in a completely different way. And what we see at the moment is that there is a merge or a change in the traditional OEMs to going more in that direction, going more software related, thinking software first, because also the business model is changing, right? And so the vehicle traditional OEMs have to react on that. And they are more business model oriented at the moment. So when it comes to mobility as a service, how the vehicle becomes an integral part of the whole value chain of a customer. So it's a different mindset. And so there's a lot of change ongoing.
And can I just quickly ask a follow-up question, Wolfgang? Is that change, is the speed of the change quite critical because of the long development time, 100 years of combustion engines? With EVs, are people coming back to the table with bigger steps, which is then impacting the other departments?
That's absolutely right. The speed of change, how we see it at the moment, is incredible, right? And of course, if we talk, so there is 100 years of development in, so there's still a lot of innovation also in the combustion engine. But of course, the degree of change is smaller than the change how it comes by the new technologies like electrification. And the market is really competitive, right? There are new entrances. There are startups, they're building cars. There is also now Tesla, which is a very established player at the moment, but it comes also out of nothing, right? So there is a tremendous pressure on the traditional OEMs for the speed of change and the speed of innovation. And that means at the end of the day, they have to go completely new ways in their traditional development approach.
Let's look at development of a car. Now, why is it important to reduce development time?
Martin, I will take this question. Reduced development time or time to market is key to be competitive in a market with very high product diversity and a high number of new companies entering this market. If we think back to the 80s, the diversity and the functionality in vehicles was much lower, innovation much slower. Nowadays, also the expectations of our customers are changing much faster, which is a further boost in frequent updates of software functionality, which is a further driver for reduced development time or time to market. Reduced development time or minimized time to market is key to survive in this change of the automotive industry.
Only a few years ago, I couldn't have imagined holding a phone like this in my hand. Overnight, Apple will send an update, and all of a sudden, I have lots of new features. So Rainer, is there you say that your customers are wanting new things at a faster pace, but also their customers, as in the end consumers, are they expecting more as well? So are you seeing that come through with your customers?
Absolutely. And update over the air is getting more important also in the automotive industry. Beside the functionality, which is also important for the customers, we also have to think about the safety in this certain. Especially here, I think this will be a topic where we have to invest a lot of effort to make this car safe, but also give our customers the chance to get new functionalities every day.
That's interesting. Let's talk about, just learn a little bit more about how the auto industry landscape is changing, and particularly with EVs. And when I say EVs, let's also include not just pure electric cars, but let's talk about hybrids, plug-in hybrids, soft or mild hybrids, 48-volt systems, even fuel cell cars as well. How much is the auto industry landscape changing as we add batteries to our cars?
So maybe I take this question. So I would like to start again a little bit from the vehicle manufacturer's perspective. We see here, let's say, two interesting streams. First, we have the traditional OEMs that somehow come from the conventional field, and they are like step by step translating from conventional to hybrid to electric and to fuel cell cars and applications. And then on the other hand, we have like these new and wild entrants and startups that directly enter the e-mobility market. And both of them have different challenges and also different strengths, I would say. For example, these newcomers, they have like intrinsically already a more software and data-oriented approach, and not like traditional OEMs, more hardware-centric, and they have this right from the beginning. And then besides looking at the perspective of the vehicle manufacturer in terms of automotive industry landscape, there is also a huge change which addresses like the overall energy infrastructure and e-mobility, I would say. So we see that EVs are actively integrated into e-mobility, into green energy concepts. If you think about charging and this infrastructure, the grids, and so it's a complete ecosystem that is enabled by electric vehicles and electrification that was not there before. if we think about traditional conventional approaches. And this, on the other hand, also leads to completely new business models, also cross-industry, where vehicle manufacturers start to thinking about talking to energy providers, insurance companies, fleet providers. So there are actually new interfaces by enlarging the automotive industry to electrification.
How do we account for car makers having not just tools, they've got their own tools, their own ways of working, they've all got their own suppliers, their suppliers all have their own tools and ways of working. How do we account for all of those variables?
I see there are two challenges, right? So you described very well the challenge out of the development process. So how our customers or the OEMs are developing vehicles, which tool they're using. And you're right, it's absolutely, they're using so much tools, different systems, so it's a very heterogeneous landscape, right? But there is a second challenge which leads to a conclusion where we'll come later on. And the second challenge is really, as Veronica described before, right? You have this, the vehicle manufacturers have to develop so much different technologies in parallel. So classically internal combustion engine, hybrids, fuel cells, full battery electric vehicles. So you have on the one hand side the development process with all these tools, right? On the other hand side, you have these many new technologies, or also ADAS, autonomous driving. And the way out for these two challenges, how we see it is really that we see the vehicle development process as an ecosystem. So also, as Veronica described, the ecosystem from end customer perspective, also development process itself, you can see it as an ecosystem. And that's exactly what we are doing, that based on the actual landscape, on the actual tools, what different departments are using, they are at the moment, or most of the times at the moment, are disconnected. Of course, they are the common process, the common goal is the vehicle development process. But right, the tools today are not interconnected. So what we introduce to overcome that is a kind of, we call that interoperability layer. You can see it as a connecting layer, like a big plug distributor where you can plug in the different tools, and which is the kind of interoperability layer that now the different tools can really work together and exchange informations. So we talk here about the coupling of simulation models, for example. So the idea is that out of this heterogeneous tool landscape with these adapters, you can create a virtual prototype. So that means you take your tools as they are in the simulation area, plug it together to a virtual prototype, which represents all the functionality what the real vehicle shows at the end of the day. So for example, at ADAS, right, there are so much scenarios what you have to test. You will never do that with a real prototype. So you need these virtual prototypes. And these virtual prototypes are now are connected by these different components as they exist. And what we also do to have it consistent, you can take this virtual prototype, which consists at the early beginning only of simulation models. You can take the models out and you can plug the real hardware in. So imagine you have the real e-motor or the real battery really available, maybe on a test bed, and we augment these real components by virtual simulation models to a combined virtual real prototype. And what we provide is really this interplug system that the simulation models in the different hardware can work together, that the customer really can have a consistent virtual prototype, or sometimes there is also used the terminology digital twin. So it's a functional digital twin. So we enable this functional digital twin for our customers, which is of course in the very early phase really scalable. So you can bring it into the cloud. You can run millions of kilometers purely virtually before you really have the real hardware available. That's how we see at the moment, or that's our contribution. How the development landscape, how it is transformed from these individual systems into a whole ecosystem where everything is interconnected at the end of the day.
Actually, I hadn't thought about the virtual twin concept. That's really fascinating. Let's take that on a step then. What are the various simulation models that a company might choose to use? And are they all operated independently, or do they work together?
That's right. Traditionally, they're really working independently, right? When we talk about virtualization means, of course, to describe the reality with a model, right? And the typical thing is to have a physical approach to create such a model. And the situation in physics is, there is, in the real world, you have one vehicle, right? And with this one vehicle, you have every physics of what you can imagine is there, right? You can investigate the NVH, you can investigate the crash, you can investigate the thermal management, you can investigate fuel consumption, whatever, right? But in the virtual world, you have now different virtual prototypes, because in physics there are these different disciplines. You have finite element methods, you have computational fluid dynamics, you have 1D simulation. So there is a lot of different languages how you describe it, right? That's maybe how to say. And what we introduce now within our interoperability layer, it's what we call a connect toolchain. Now you can connect these different physical approaches to this virtual prototype. So in this virtual prototype, or you can call it digital twin, right, or functional digital twin, you can really see that's a direct comparison to the real vehicle. So you can do the same things with this functional digital twin as you do with the real vehicle. You can investigate crash, you can investigate fuel consumption, you can investigate all of these things. One example is, because we talk about EVs or so, right, one special focus theme, what we see at the moment, is really the battery. The battery is a little bit a key component, and also for the battery, we can provide to our customers now this functional representation of the battery over the whole process. So there's really, you can see it as a dysfunctional digital twin lives over the whole process. It's like a second life, right? It's like a second life in a virtual way. So you have the real component and you have the second life in the virtual way. That means this digital twin also lives if the vehicle is already on the road. So if the battery is already at the end customer, and the key thing is that there's always an inter-exchange between the two worlds, right? That the real world is used for making the digital twin better, to come closer to reality. And then with the digital, in the digital world, you can scale. You can drive different scenarios and in different driving conditions, different ambient conditions, and so on. So it's really, at the end of the day, how we see it at the end of the day, and now coming back also to the ecosystem, to provide then a consistent view, so to really transform the real world in the virtual world. And at the end, it's really a combination.
So how does that work? How do you collect data?
You mentioned a big challenge, data. Which is at the same time a big potential, which is sometimes underestimated, sometimes not. So actually along the development process of components, of vehicles, and up to the in-use phase, we have huge amount of data, like data sets, time-based data, metadata about batteries, e-motors, all the components, material data. So lots of information actually. And what we see when also working with our customers from the past and most of the times currently, this data treasure is actually locally stored on laptops, and each team or maybe every person has its own way of storing data. And also, if you think of vehicles on the road, we have these onboard data loggers that you would have a look at on demand. Which is a process that works in principle, but there is a huge potential that you can gain actually if you link all of these data sinks and sources. And this is why we, together with our customers, are working on this. We developed an IoT standard. We call this like Data Connect, where we link the data along the development process between simulation and experiment, also link it with expert knowledge, keeping in mind also applications for vehicle to the cloud, to overall actually increase the development efficiency. and at the same time also the quality of the products. And this again opens completely new areas and business models.
And you mentioned that you can collect data, and I like the idea of a treasure trove of all of this data and making sense of it. What sort of things can you collect data on?
The data that we're collecting along the vehicle development process is, on the one hand, measurement data, simulation parameters, metadata, material data, also in-use data, so actually data from, for example, batteries, e-motors, from vehicles at the end customer. And this actually adds a value by combining this with data analytics approaches. One example, we have already mentioned the battery, where it is very important to collect different data also at different stages, is like thinking in terms of a battery life cycle management. So here it's really about linking different parties, different stages along the battery value chain, from raw material to battery and vehicle development process, way up in the in-use phase, which is like the first life of the battery, but finally also the second life, and then through recycling, repurposing, you bring it all back. So this is actually a very good example where all of collecting data are getting more and more important.
Why is it important to make that data available to multiple departments across an organization?
As Wolfgang already said, we are now facing with more than 1 century continuous further development of the processes and technologies. We also heard that new technologies we have to face with, but we also have to think about how we can bring further added value to the development process. It's all about making development relevant decisions earlier, faster, cheaper, and better. And this is only achievable if interdisciplinary communication and teamwork will come together. Engineers from different genres have to share testing, simulation, and prototype resources. That's the reason why finally, beside the technical aspects, we have been developing solutions which support connecting the people. Cross-border collaboration is key.
But let me ask you maybe a silly question. If two teams are working independently, so if Team A is making a part and Team B is making a part, those parts seem to be totally independent, or traditionally were very independent before EVs. How can they communicate, and how do those teams know if in some way those two parts are going to interconnect?
That's, Martin, a very good question, and a very natural question. It's at the end, what with this interoperability layer, what we discussed, you can see this interoperability layer also as a kind of collaboration framework, right? That enables something. It enables to build these digital twins. So imagine, as we have this podcast now, we build together a virtual vehicle, right? Martin, you provide the engine, and I'm providing the gearbox, and Rainer provides the battery, and Veronica the chassis, and let's imagine we build the car together, right? And that's really, when I say we build the car together, it's really this digital twin which represents the vehicle, right? I can use it, Martin, you can use it, Veronica and also Rainer can use it. And if now Veronica changes something in the chassis, or Rainer changes something in the battery, because maybe they see we need a bigger size because the EV range is too low, then this is conserved in this digital twin. So if I use the digital twin now, I see, there's some change in the component. Rainer changed the size of the battery. That means I can see then immediately the impact on the gearbox, for example, or maybe I also have to change something in the gearbox. Or if I change, or you change something in the e-motor, Martin, also we will see then together as a team in this collaboration environment, maybe there is now a different performance of our virtual vehicle. And that's exactly is making the difference. This collaboration platform, which enables to build this functional digital twin, is like as we drive in a real car. In the real car, you will see it immediately, right? If something increases the size of the battery or the size of the e-motor. So the idea is really to introduce this collaboration platform, which of course has it's a functional thing, but at the end of the day, it's more about bringing people together. That's the key.
We're recording this podcast at halfway through 2020, so many parts of the world went through a version of lockdown or staying at home, and so virtual sport took off and people were at home, they were playing virtual racing. But now Austria hosted the first 2 Formula One races. Real racing is back, but we don't see those two mixing. People were either at home on their simulator or they go out racing on the track in real life. So those, I understand, are very separate, and the two don't mix. You don't have real racing drivers also competing with virtual racing drivers in the same race. But we need to in the race of making a car. And I understand now that we need to mix those two things. So how does a virtual and a real environment work together?
That's a perfect example, Martin, now with Formula One. So we're all happy that Austria hosted the first 2 races in reality, but we are sure. We also, of course, have a lot of activities in racing, and there will be in the future, of course, an augmentation of the real race with the virtual race. I'm sure about that. So you have to do 2 things, right? You have to bring the real vehicles into the virtual world, and you have also, you have interconnection of them. So what we are talking here is about to augment something, right? It's not about artificial. We're doing not artificial things, real or virtual. It's really augmentation. And now transferred this, your example from racing to the development process means the question for what we see in the industry is, how to introduce or make it real in the development process. And it is on the one hand side a change. And what we also see, the change does not work it's not a big bang. You cannot say, okay, tomorrow we mix the worlds. It's a step-by-step approach. And that's why what we provide, for example, is also what we call building blocks. So we have connecting building blocks. For example, we have a building block which connect models. We have a building block which connects the different data sources. We have building blocks where you can connect the models to the real testbed or to the real components. And we have also building blocks to connect devices. For example, devices. The device could be a vehicle, right, which produces data and brings that back into a data center, for example, and maybe is used for updating a model. So the answer to that is really, at the end of the day, we're talking about software. So we have software building blocks, which enables a step-by-step marriage of the real and the virtual world. And it's not, as I said before, it's not a big bang approach. It's a step-by-step approach. That's how we dealing with the topic today and supporting our customers in transforming their development process.
Taking that logically step by step, at the end of the journey, can you ever completely stop real-world testing?
Thank you for that question. A clear no from our side. Finally, every car has to be validated in real world before it gets to mass production. Sometimes this is even caused by law. We are working on solutions to enable development work based on real-world testing in early stages of the development process. This became possible via flexible combination of real prototype parts and vehicles together with simulation models, also called functional digital prototypes. Nowadays, this is even proven for high dynamic phenomena like drivability optimization and real-world energy consumption performed on different testbed types. You can already buy vehicles out there where these methodologies were used during the development process.
How quickly can you get that feedback? So, as you say, it's a hard no. There will always be real-world testing, and if I simplify it in my brain, a test driver goes out and tests the car, comes back and tells the engineers what happened. I know that's not reality because there are many thousands of sensors all over the car, but obviously there's the human feedback and then there is data collection. But how quickly can you bring all of that together and then input that into a virtual environment to then start virtualizing different scenarios?
To answer your question pretty fast, in some cases even already in real time over the air. More details about that by Veronica later. One example is the thermal management optimization of electric vehicles. Thermal management is very important for electric vehicles because it influences the lifetime of a battery and also strongly influences the electric range of the vehicle. We are already able to set up a test environment just using the battery as a real component. The cooling system, the vehicle, and the environment, including driver, were simulated. With this setup, the thermal management could be optimized before a first prototype vehicle was even available. Vehicle tests later in the process showed a very good correlation. In special operation areas, the vehicle data was used to increase the model quality. Further optimizations could be done without using the expensive prototype vehicles, as already explained by Wolfgang. Just another example to reduce the number of expensive prototype vehicles, as well as to shift development tasks into early stages of the development process.
You could make a prototype vehicle, you could make 40, or you could make 100 of them. But what about if you sell 20,000 cars to your customers and they're all driving them around and collecting data? Now, presuming those customers or all of those consumers agree to sharing that data, and I'm sure we're all familiar with that. We do an update on our Windows and it says we would like to send diagnostics back to Windows. Yes, okay, if it helps. Tell me about in-use data collection.
So that is actually a very hot topic at the moment. Let me first a little bit explain what we mean with in-use data. So we're now here talking about electric vehicles that are on the road and our end customers or fleet operators or e-mobility providers. And we're, as you say, we're not talking about one single car out there. We're really talking about hundreds and thousands of vehicles out there on the road. The data that we collect could, for example, be data from the battery management system on the CAN bus or any kind of other component data or vehicle data. And so traditionally, our OEMs and the development process was not so much driven by in-use data, but nowadays we see a huge trend to actually making finally use of this in-use data. And what we see from our interactions with our customers is somehow three big applications for this in-use data. So the first would be take this information, let's say, back into the development process. So learn from this data on the road to improve your development. The second application is optimize the operation. So depending on how these vehicles are used on the road, you can, in principle, in real time, give recommendations and optimize operations. And the third big application field would be looking into future by doing predictive maintenance.
Yeah, that's interesting. I like the idea of my car telling me that before something goes wrong, maybe get this checked. Let me also, so the next question, let me also, I like motor racing, so I find it very easy to find examples. A team turns up to a race and says, oh, we've done lots of work in the wind tunnel or on the CFD, and the car is great, and they go out and qualify and they're at the back of the grid, and the excuse is always, well, the correlation is bad between the computers and and what ended up on track, and there's always an excuse. So how do you make sure that real world data, what's actually happening on different road surfaces or different weathers, different temperatures, how does real world data with so many variables compare to, if I call it lab data, like the sort of the perfect scenario? How do you take those variables into account?
So the experience which parameters are needed, as well as how to organize them, has been gained in the last decades. Nowadays, we are even able to have a good correlation between tests on the testbed with embedded simulation compared to vehicle tests. This is even for very dynamic topics like drivability, able up to a quality that experienced test drivers are not able to feel the difference between real vehicle optimized data and data updated on different testbed types. Just to give you an example from the racing, our testbeds are used for optimizing lap times with Formula One cars, where all the lap, the driver and so on is simulated, or we have a real driver based on a hexapod, and this is used long before real testing on a test track is possible or allowed.
Let me add something, Martin here maybe. We're using here also special technologies, what we call Model Factory, which is using some, nowadays you will call it artificial intelligence, right? But we like more augmented intelligence because it's augmenting something, right? So with this Model Factory approach, right, so we're using mathematical algorithms which are continuously in a loop. Where the real test data is used to update the model, and then to guarantee for the next development or for parallel developments to use good models. So it's really a kind of training area of the models, right? And if they are old enough, right, or mature enough, you can use it. And of the example of Rainer, and that must be done, especially in racing, very fast, right? If you have two stints or between two training sessions, you have to do or you have to be able to make thousands of simulations to be ready because maybe you have a time slot of 2 hours where you need the new setup.
The EVs that are on the road this year, this is a big year. Next year's a big year for many OEMs releasing exciting electric vehicles. But we know that those cars, over their life, will get better. They will be improved. They'll have new features added to them. How has over-the-air updates changed the role of data?
Over-the-air updates, what does it mean? So we're having a communication from vehicles and back into vehicles. We're collecting data, analyzing it, maybe apply algorithms, digital twins, all of this that we just mentioned, in order to add a value and send this information back. This is called backflashing. Now, again, if we think about historical vehicle development process, more or less all of the vehicle functions were finalized and frozen after completing the development. And as soon as the vehicles are on the road, this is fixed, maybe some software updates and a big service at some point, but that's it. But nowadays, as you say, there is a trend to change this significantly. So there are more and more OEMs, especially new entrants actually, that are actually completing some of their development tasks in the in-use phase by doing over-the-air updates. So maybe for some components, they have a mature base calibration and basic principle, but they're still applying updates while the vehicles are used on the road based on the functions that they see on the road. Like a very simple example maybe would be windshield wipers. These are updated over the air. But then there can be more complex updates, like really changing limits on the battery management system in order to improve battery performance or even extend the battery lifetime. And so over-the-air update in this case is a part of the story that can help you in order really also to predict battery life and extend it. And in general, it helps to have like a continuous development and learning from the road.
That's exactly the case, Martin. Update over the air will change everything, right? It changes the business model, or it could change the business model, right? It will have a deeply impact in the development process, because the question is, as Veronika explained, if you have a new update, okay, how to test this update before it is released to the vehicles? Right, because you have to ensure the vehicle is already an end customer. How does the validation process looks like? You have to be very sure if you updated it that it really works at the end of the day. And the key thing, as Veronika mentioned, is it really enables a continuous feedback loop. So you change something in the vehicle, and you will have immediately a feedback loop on the vehicle, right? And you will see that in the data. And based on the data, you can learn and make an additional update. So it will improve, on the one hand side, the usage of the vehicle for the end customer, and also for the end customer, it is convenient. Everybody of us know it from the phones, right? You get an update, Of course, maybe you have to pay them for the updates if you would like to have a new functionality. But that's one of I think, the biggest game changer what we'll see in the future if this is rolled out in a broader way.
Well, that's super interesting, and we've learned a lot, and we're even more excited about where this electrification journey is going to go. To all of you, thank you very much for joining us on the podcast today. We will see you on the next episode. Thank you very much.
Thank you, Martin.
Well, you can find out more about what AVL do at avl.com/electrification. And make sure you tune in for the next part of our series of Tech Talks with AVL.